Imagine a snake so massive it could swallow a crocodile whole. A serpent stretching longer than a city bus, weighing more than a ton, with jaws that could unhinge wide enough to consume prey the size of a small car. This is not mythology. This was Titanoboa, the largest snake that ever lived. This is the story of Titanoboa cerrejonensis, the serpent that ruled when Earth became a furnace. And deep in the Amazon's darkest corners, where sunlight never reaches and legends refuse to die, some still whisper a chilling question. What if it never went extinct? 66 million years ago, an asteroid struck Earth with catastrophic force, ending the age of dinosaurs and collapsing entire ecosystems. In the immediate aftermath, fire and darkness reigned as sunlight was obscured by a global veil of dust. But extinction is also renewal. In the Paleocene epoch that followed, life slowly recovered and diversified. Plants recolonized scorched landscapes, insects multiplied, and vertebrates radiated into ecological spaces vacated by dinosaurs. The Paleocene climate was markedly warmer than today. Global temperatures rose several degrees, creating a greenhouse world where tropical forests expanded into higher latitudes and humidity saturated the air. In northern South America, the Cerrejón region became an enormous mosaic of rivers, flooded plains, and dense jungle. An environment where heat and moisture combined to create extraordinary biological productivity. Ectothermic animals, whose body temperatures depend on ambient heat, thrived under these conditions. Warmer environments allowed extended activity windows, faster digestion, and increased growth rates. Crocodilian relatives grew to impressive sizes. Freshwater turtles inflated to dimensions unfamiliar in the modern world. Fish species proliferated in abundance. Energy flowed freely through primary productivity into complex food webs that could support megafauna. Without dinosaur dominance, reptiles reclaimed apex roles in many freshwater and riparian systems. Natural selection favored traits that exploited abundant resources, and selection pressures tilted toward gigantism in several lineages. Physiological constraints loosened under persistent warmth, metabolic rates remained high, growth trajectories extended, and ecological equilibria shifted. In this steamy crucible, evolution tested new extremes, and within the wetlands of Cerrejón, a lineage of snakes began to grow toward unprecedented scale. The recovery after the catastrophe was not a simple return to previous forms, it was a reinvention. Flora and fauna explored ecological opportunities with a vigor born of empty niches and novel selective pressures. Rapid diversification produced experimental body plans and life strategies. Some ephemeral, others that persisted and radiated across continents. Rivers became arteries of life, carrying nutrients and creating microhabitats where species could specialize. In these channels, the interplay of opportunity and constraint shaped communities in ways that allowed the extraordinary sizes of some reptiles to be not merely possible, but advantageous. The rediscovery of Titanoboa began not in a laboratory, but in a coal mine. Miners in the Cerrejón Formation of Colombia exposed massive fossil vertebrae that confounded researchers. These bones bore proportions far exceeding any known snake. Paleontologists led by Carlos Jaramillo and Jonathan Block assembled fragments and applied comparative anatomy and biomechanical scaling to estimate the animal's size. 28 vertebrae from a single individual provided the backbone of reconstruction, literally and figuratively. Each vertebra was immense, sculpted for strength and interlocked in a way that implied a column of dense muscle. Using vertebra-to-body length relationships derived from living constrictors, scientists estimated a length between 42 and 48 feet and a mass greater than a metric ton. Such dimensions reshaped assumptions about reptilian limits. The species was named Titanoboa cerrejonensis, the Titanic boa from Cerrejón, and the find became both a scientific milestone and a cultural sensation. Museum displays and documentaries emphasized its scale, but the academic implications were deeper. Fossil plants and isotopic signatures from the same strata supported unusually high Paleocene temperatures, reinforcing the link between climate and gigantism. Titanoboa emerged not as an aberration, but as the expected outcome of a greenhouse ecosystem rich in resources. The meticulous process of reconstructing the animal required collaboration across disciplines. Sedimentologists, paleobotanists, and geochemists provided context, while comparative anatomists refined morphological models. Radiometric dating of adjacent layers constrained the timeline, and the presence of particular plant fossils indicated sustained warmth. Each vertebra told a story in its growth rings and mineral composition, and together they formed a narrative of environment and adaptation that illuminated how ancient life responded to extraordinary conditions. Titanoboa's anatomy married familiar constrictor design with extreme specialization. Its vertebral column supported a thick, muscular torso wrapped in layers of powerfully developed muscle. Constriction depended on coordinated contractions that could interrupt circulation in prey, leading to rapid loss of consciousness. The skull exhibited kinetic features common to large snakes: loosely articulated bones, mobile joints, and elastic ligaments allowing tremendous gape. Backward curving teeth acted as anchors, securing prey while coils tightened. Internally, organs were elongated to match the serpentine frame. A dominant, elongated lung maximized gas exchange. Digestive glands produced potent enzymes to dissolve tough tissues and bone. Sensory systems focused on chemical and thermal cues. A forked tongue sampled the air, delivering scent particles to Jacobson's organ, while heat-sensitive pits would have assisted in locating warm-bodied prey along shaded banks. In water, lateral undulation enabled silent, efficient locomotion. In bursts, the snake could accelerate to seize prey by surprise. Despite its power, Titanoboa existed near the biomechanical ceiling. Structural stress, respiratory constraints, and enormous energy requirements meant its success depended on sustained environmental abundance. Consider also the biomechanics of feeding. The coordinated peristaltic motion that moves a massive carcass along a snake's body requires precise timing and force distribution. Musculature had to be resilient to tearing forces and reinforced by connective tissues to prevent catastrophic injury during ingestion. Vascular adaptations probably supported temporary spikes in circulation during digestion, shuttling nutrients to a body stretched by an enormous meal. Bone microstructure indicates long, repeated growth phases, suggesting individuals invested years, even decades, in reaching full dimensions. In the Cerrejón wetlands, Titanoboa reigned as apex predator. Rivers braided through sediment-laden plains. Shallow lagoons and backwaters provided hunting grounds where concealment was abundant and visibility poor. Giant turtles, such as carbonomes, armored and heavy, gorged on vegetation at the water's edge. Crocodilian relatives patrolled channels with lethal jaws. Massive fish churned the muddy depths. Within this crowded arena, the serpent exploited opportunity with ambush tactics. Concealed beneath tannin-dark water or coiled along submerged logs, Titanoboa waited. Sensory acuity tuned to vibration and scent allowed it to detect approaching prey in near darkness. The strike was sudden. Jaws snapped, coils wrapped, and constriction commenced. Rather than merely suffocating, constriction interrupted circulation, collapsing blood flow and leading to rapid unconsciousness. Once subdued, the prey was swallowed headfirst through coordinated muscular waves and gradually processed by powerful digestive acids. A single massive meal could sustain the snake for weeks or months, reducing the need for constant hunting. With no predators capable of challenging its size, Titanoboa shaped prey populations, influencing behavior, distribution, and even vegetation through trophic cascades. Its dominance translated into ecological control across riparian landscapes. Ecological interactions extended beyond simple predator and prey. Titanoboa's presence affected nesting patterns of turtles, movement corridors for herbivores, and even the behavior of smaller carnivores that avoided prime hunting sites. Scavengers likely tracked feeding events, capitalizing on leftovers from rare but massive kills. The snake's role as a top-down regulator would have reverberated through trophic layers, influencing nutrient cycling and habitat structure in profound ways. Daily life for Titanoboa revolved around heat and timing. Each morning it relied on thermal sources, sunlit banks, shallow thermal eddies, or warm river margins, to raise body temperature to levels that supported activity. Ambient temperatures around 30 to 34 degrees Celsius allowed efficient metabolism, quick digestion, and extended activity periods. After feeding, the snake entered long digestion phases during which it was less mobile and more vulnerable, retreating to secluded refuges while enzymatic processes consumed its meal. Reproductive behavior likely mirrored large modern boas. Females producing sizable clutches of eggs in protected nests, hatchlings left to fend for themselves, juveniles facing high mortality from crocodilians and other predators. Growth to full size likely unfolded over decades, an incremental accumulation of mass sustained by periodic large meals. Seasonal patterns influenced prey movements and breeding cycles. Storms reshaped channels and redistributed nutrients, while sustained warmth and high productivity maintained abundant food webs. In this context, Titanoboa's gigantism was not a quirk, but a dynamic life history outcome responsive to persistent environmental conditions. The daily rhythm of life was punctuated by long waits and occasional explosive action. Titanoboa would have spent much time motionless, conserving energy, attuned to the faintest ripple or scent. When prey appeared, muscle and nerve fired in coordination accumulated over evolutionary time, producing a strike both graceful and lethal. Nights in the Paleocene wetland were thick with insect choruses and the distant calls of primitive mammals, while the air carried the musk of wet earth and decomposition, a sensory backdrop to a world where life and death played out in cyclical intensity. Earth's climate, however, is never static. Following a final spike in warmth known as the Paleocene-Eocene thermal maximum, global temperatures began a long-term trend toward cooling. For organisms adapted to relentless heat, even moderate declines in ambient temperature had severe physiological consequences. As temperatures fell, metabolic windows narrowed. Digestion slowed, activity budgets contracted, and energy deficits emerged. Titanoboa's capacity to grow and reproduce diminished as environmental support waned. Over generations, populations thinned as individuals failed to reach reproductive sizes and prey bases shifted. Extinction proceeded not as a single dramatic event, but as a gradual erosion of favorable conditions. Fossil layers record a changing assemblage, fewer megafaunal remains, altered plant communities, and an ecosystem trending towards smaller-bodied, thermally flexible species. Titanoboa faded from dominance as evolutionary trajectories favored adaptability to cooler climates. As the planet cooled, ripple effects cascaded through ecosystems. Plant communities shifted towards species adapted to cooler, more seasonal climates. Insects and smaller vertebrates adjusted their life cycles, and the prey base for large predators changed both in abundance and composition. These gradual transformations altered selective pressures. Traits that favored extreme size became liabilities. Over evolutionary time, the balance of costs and benefits moved away from gigantism. The remnant populations of large reptiles dwindled, confined to fragments of habitat where heat and prey persisted only episodically, until even those refuges diminished. Legends of giant serpents persist in human culture. Indigenous Amazonian narratives tell of river monsters and long-bodied spirits. Modern anecdote and occasional sensational reports sometimes revive speculation about hidden giants in remote waterways. These stories tap into an ancient psychological wellspring, awe of the enormous and fear of what lurks unseen in dark water. Scientific evidence constrains these fantasies. Titanoboa's size required sustained Paleocene thermal regimes that no longer exist. Contemporary tropical climates, while warm relative to human comfort, do not provide the constant, elevated temperatures necessary for ectothermic megafauna of that scale. The largest living snakes, reticulated pythons, and green anacondas, approach impressive lengths but remain far smaller in mass and ecological impact. Sustaining a population of Titanoboa-sized animals today would demand continuous regions of high ambient heat, abundant prey biomass, and minimal human disturbance, conditions that are effectively absent. Satellite imagery, ecological surveys, and decades of field study have drastically reduced the scope for undiscovered megafauna in the accessible world. While new species continue to be described, the likelihood of a surviving Titanoboa is vanishingly small. Myth and science therefore follow different logics. Myth amplifies human emotions and memory, while science demands empirical support. The persistence of Titan snake tales tells us more about human psychology than about undiscovered fauna. Still, these narratives inspire curiosity and motivate fieldwork that often yields surprising discoveries. New frogs, insects, and even previously unknown mammals, though not the world-shattering rediscovery of a vanished megafauna. Titanoboa vanished not in sudden violence, but through climatic change that reshaped the world it had mastered. Its fossilized bones serve as a testament to life's capacity to expand when conditions allow and to recede when those conditions change. The tale of the Titan snake reminds us that dominance is conditional, bound tightly to environmental parameters that may shift without warning. Paleontology offers humbling perspective. Species flourish and fade as Earth experiments with new climates and ecological configurations. Titanoboa endures in stone and story, a symbol of nature's capacity for wonder and an admonition about the fragility of ecological balances. We study its remains not simply to marvel, but to learn how life responds when the planet's rules are rearranged. Beneath the canopy, life moved in slow, often invisible patterns. Morning light filtered through layers of broad leaves, turning droplets of water into jewels and releasing the scent of decaying plant matter that braided with the perfume of fresh growth. Towards midday, the air thickened, heat shimmered above the water, and the smallest ripple could mean salvation or death. On one particular bank, a juvenile Carbonemys crept to the edge to graze, unaware that a massive coil lay within the murk. The moment between awareness and capture was measured in heartbeats, a shift of muscle, a half-second of vision, the thunder of crushing force as coils tightened. For the turtle, there was no malice, only the blunt calculus of survival. For Titanoboa, the event was routine, another episode in a life governed by hunger and thermal opportunity. These micro-episodes repeated across the landscape countless times, each feeding into the slow churn of nutrient flows and population dynamics. Observing them from a distance, one perceives both brutality and a peculiar efficiency, an ecosystem operating with a tight economy of energy and time. The rhythm of feast and famine echoed through generations, shaping bodies, behaviors, and the very course of evolution. Dramatically,